final speaker on our panel is Maurice Roos.
Thank you, and thank you for inviting me to run through rather quickly some water geography for California. This map has two things on it: the average annual precipitation, which is less than 10 inches in big parts of the southern portion of the state, up to the orange, which is more than 50 inches. And the orange areas are up in the north coast and the Sierra Nevada peak. The blue arrows are to scale the size of the average annual runoff, which is about 70 million acre feet. About 40% is in the north coast area. About 30% would be from the Sacramento Basin. So what this shows really is that about 3/4 of the natural water supply is north of the Delta. And if you look at the requirements for ag and urban purposes, about 80% is south of the Delta. So that's tells you a lot about why we have the big water transfer works in the state. Others have showed this slide, but this just kind of shows where the major facilities are for aqueducts and canals. What is noticeable is that we're shifting water from north to south and from east to west. Most of the Bay Area supply comes from east to west. And we got the Owens Aqueduct north to south, and then the Colorado River for Southern California, also east to west. The water in the north has to go through the Delta, and Matt kind of gave a little bit of summary of that. So right now it goes through these Delta channels on its way to the big pumping plants. Some of the water is migrating to the west side of the Delta. There it can become salinized by saltwater intrusion from the San Francisco Bay if the outflow isn't sufficient. Now, it's not a steady movement because you've got the tide going back and forth about 8 to 10 miles. So that's what promotes the mixing. But there's a risk in using the Delta for supply because so much of the land is below sea level. And there's concern that since many of these levees are rather weak, built on peat soil foundation, that someday there may be a collapse. If it happens in the summertime, there'd be a strong interference with water transfer. And the other factor is sea level rise. This is the 100-year or so history of the average sea level at the Golden Gate. And if you're wondering why we use 19 years, it takes the moon 18.6 years to go through a cycle, so that kind of evens that out. The little spikes are the big El Nino years when the ocean tends to rise along the coast. It's come up about 0.6 of a foot during the century, or the rate would be about 0.7 of a foot per century. But for some strange reason, the last 20 years, it's flattened out, and I'm not quite sure why. But it definitely has gone up. This is from the new report of the National Research Council's panel. The value for California is I guess I'll call it orange, and the dot represents their estimate of the middle. So they're predicting quite a strong acceleration. This would be about a foot in 2050 and 3 feet in 2100. And that could be a real problem in the Delta, let alone places along the bay. So that's one of those changes. Now to try to give you the overview of where the water comes from, where it goes, where it's used. Most of it is natural runoff, which also forms some of the supply for recharging groundwater aquifers. A nice slice from the Colorado River, and some little bit of inflow from Oregon, some from land use changes, and probably 1.5 million acre feet would be an estimate for the net groundwater overdraft. Where it's used, depletion would be the consumption of water for growing crops or for urban areas, and it's lost in the system either through evapotranspiration or goes to the salt water. So we've got that over there. Quite a bit is remaining in streams statewide, But a lot of this is locked up in the North Coast Wild and Scenic River Program, which is just the natural flow. It doesn't take storage for that. Required minimum delta outflow. And that leaves you with other North Coast rivers that from a practical standpoint aren't really available for development, I don't think. They're just too far away or too flashy. And then we have the big floods. Those too will never contain. So, but I think there's still about 3 million acre feet that could be developed. And that would mean, more dams, more canals, that kind of stuff. I think Tina's probably described where it goes. Segments about 45% environmental, this is consumption, urban 11, ag 44, or a 20 to 80 split that way. Another point to bear in mind is that we are highly variable as far as runoff goes. This is the Sacramento River runoff. It's the color code is for the 5 categories of years that are used, blue being the wet ones and the red being the driest or critical. I call your attention to the 2-year severe drought, 76-77. Not too much later, the 2 wettest years in the record, 82 and 83. The 6-year drought from 1987 through 92. And the 3-year drought, not quite as bad, that was mentioned also previously. So we not only have a lot of location issues, but we've got a lot of variability. Comparing some of the droughts that we've had in the last century, I've used colors for a 6-year drought. Notice that 2 of them in the 30s and here in the 70s, or in the 80s, I mean. It's severe 2-year drought in the purple. And then a more common interval seems to be 3-year drought. And off on the left, next to the average runoff, is something that we've determined from a 1,000-year reconstruction of Sacramento River runoff from tree rings. And that one is, for 3 years, almost only about half what we've seen the worst of in the last century. So things could get worse, even from the record. Well, I want to go quickly over some potential for new water supplies. We've heard already about reducing water demand for urban agricultural purposes, but I want to caution here that it's the depletion that counts, the actual consumption of water, not the applied water, because a lot of water in interior areas is being reused. The excess from one farm goes into the stream and it's available for somebody downstream to use. We talked about improving operational efficiency and transfers, and there the big problem would be the delta, which you've heard about already. I don't think there's a whole lot of new supply available, except for some works in the delta. So what I'll go over quickly then is the ideas that we have that could increase water supply. And the first one is surface storage. The next one is conjunctive management, the surface and groundwater, which is actually in practice. Santa Clara County does a lot of this in the Bay Area. And then desalting, precipitation enhancement or cloud seeding, and then recycling municipal water. Looking at the CalFed program, they had 5 reservoir proposals for new storage. The first one is enlarging Shasta Dam, raising Shasta Dam up to maybe 18 feet. The next one down would be the west side off-stream storage in the Sacramento River system. The third would be in-delta storage. This would be the idea, since we've already got islands that's shaped like bowls, flood a couple of them and use that storage, pop them out. One of the hitches with that is that you pick up additional organic compounds, and then you've got more of a problem in treating it for urban purposes. Los Vaqueros enlargement has been proposed, and actually it's already been enlarged once by Contra Costa County Water District. The Los Banas Grandes Reservoir, it's the next valley south of San Luis Reservoir. Here the problem is, how do you get the water from the delta to fill it? with all the restrictions on pumping. There's enough aqueduct capacity. And then Auburn on the American River east of Sacramento had been proposed. Good water supply, a lot of storage. And then there's probably a list of little ones, like Merced Irrigation District is looking into raising their spillway gates 10 feet. That would give them 70,000 acre feet. One of the issues there is that it'll back water in a few years back into what's the lower end of the Wild and Scenic River area. I think East Bay Mud is somehow, there we go. The principle of conjunctive storage is that you would draw more on your surface reservoir during a wet year and put part of it in the ground in a spreading basin. The rest goes to 30 for demand. In a dry year, you don't get as much out of the reservoir, but you pump the groundwater back. And notice the demand's about 10% higher in a dry year. So you need a little bit more. On weather modification, this gives you the areas that have had some kind of cloud seeding operation going during the last decade. Not all of them operate every year. In fact, some of them haven't operated very much. But we think it probably produces about 300,000 acre feet per year of new water. It's seeding the clouds mostly with silver iodide, sometimes dry ice, to slightly increase the efficiency of the natural precipitation process, mostly for snowpack. This is a picture of one of the cloud seeders that's used in the Sierra watershed. It's got a propane-based flame that puts out a smoke, you might say, of silver iodide particles. There may be about 300,000 acre feet more available if we were to do some of the other watersheds, primarily in the north, at least with present technology. Briefly, some of the climate change effects. The big one would be shift in runoff patterns, more winter runoff, less spring and early summer runoff due to smaller snowpacks. Sea level rise, and that's got its levee and salinity problems in the Delta and other low coastal areas that you saw already. Bigger floods due to larger winter rain flood producing areas during a storm, and more water vapor in the storms themselves. Somewhat higher crop and landscape water needs, and water temperature problems for cold water fish. If you've got a warmer atmosphere, the streams are going to be a little warmer. One that might go on here too might be more an increase in forest fires. Looking at three curves for the Sacramento River system, the blue is the precipitation pattern, the average. It looks sort of yellow from here is the runoff pattern, the natural runoff, and the red is the pattern of demand. And what you can see is a lag, and that lag is because some of this precipitation comes as snowpack, and that then melts in the spring, causing the runoff. So if we didn't have as much snowpack on the McKellamie River, for example, you would see what is now quite a snowmelt peaking stream, and the water would shift back. This would be an estimate for what would happen with 3 degrees Celsius climate change. So you get more runoff in the winter, less during the spring when you need it. And you say, well, we'll store in the winter. But wait a minute, we need that winter space empty for a possible flood. This is Folsom, but they all look somewhat the same. So most of the time, some of this excess runoff in the winter during storms will wind up having to be dumped. And so it does have a cost in water supply. There's a picture of the molten weir in the Sacramento River flood system overflowing. The excess water from the river is pouring into the Butte Basin in this case. And here's the annual 3-day maximum flow for the American River east of Sacramento. And again, the trend seems to be there that we're starting to see bigger flood-producing storms. So there's two reasons here. One is because if you raise a snow line, you've got a bigger rainfall runoff contributing area. The other might be the intensity. And since this is the big area, I got to leave you a protest picture. Protest March of the Snowman.